welcome everyone. It's our last session of this tranche, and what better way to have Ezra across from the States giving us a presentation, an introduction, an overview to CICS internals. So Ezra, I'll leave you to it. You have the room, and best of luck.
Okay. I'm noticing I'm having a little video trouble, so I'm going to shut off my video for now, but I'll put it on toward the end. So can you see my screen, Rob?
I can, but I was on mute. Yeah.
Yeah, good. That's all I needed to know. Good. Well, good afternoon, I guess, for you guys. It's morning for us here in the U.S. It's really weird. I'm used to being there on site, you know, and enjoying the lovely English weather at this time of the year and the fireworks and whatnot. So hopefully next year. Anyway, this morning I'm going to go through an introduction to CICS internals, right? So we'll talk a little bit about how CICS is internally structured, and this is the agenda I have for this morning. I'm going to start by a little overview of the CICS structure itself in terms of domains and what we had before and what we have now. And then a little bit about how domains communicate, right? We use these things called domain gate calls, which you could think of as a link with a COM area. And then some of the key terms associated with domains, like encapsulation and the different types of calls that are available and the way those calls are formatted. Talk a bit about kernel linkage and passing data between programs and how stack entries work. And then toward the end, I'm going to go through some of the core domain control blocks, right? So we're going to talk a little bit about kernel, dispatcher, transaction manager, and AP domain, right? You'll notice I skipped over storage manager, not that I won't talk about it, but the kernel, dispatcher, transaction manager, and AP domain make up the core of an application running in CICS. And then we'll open it up to any discussion at the end, assuming we have some time. And so that's what I plan to do. So anyway, CICS has been around for quite some time. I would have loved to have been able to say it's older than me, but I'm just slightly older than CICS, right? Came out in 1969, even though it was reasonably well structured. The design at the time, the computers available at the time made it such that everything was kind of managed through this management module type interface. So similar to the way we'd write applications today, right? You'd write an application, and I guess within the world of CICS, it would be a management area, right? And then it would have its own data, which would be its control blocks. And because all the people that were writing different areas of CICS were probably working all together, they knew a lot about how the internals of one particular management module worked versus another. Well, what we found out was over the years, as they started upgrading and adding features to CICS, that became more difficult to manage. Some of the problems were that one domain developer could read well, it wasn't domains at the time, right? It was management modules, but one developer could actually go into another developer's control blocks, either take data out of it or modify some of the data in it. And if you were around back at the old CICS 1.7 days to 2.1.1, that was a very hard transition. Took for me a couple of years because we kept running into internal problems that had nothing to do with our applications. So anyway, in the early 1980s, IBM started this process of restructuring CICS, right? Effectively separating out the management structure into these things called domains and applying certain rules to those domains, like encapsulation. So we'll talk about that through this morning, and you'll get an idea of how that worked. So this is what we draw as the domain architecture. And what you're seeing here is a history over time of the domains that were created. Now, again, remember, CICS existed, right? The domain and the first release that came out, right, which was 3.1.0, which is a lot older than the last release, which was 3.1.0, separated out CICS into 16 general purpose domains. So that's the top two lines you see here. And effectively what they did was they took the entire old product and they said, oh, whatever we can factor out into a separate domain, we will. And whatever we can't separate out, we're going to stick in this thing called the application domain. And if you go back to that period of time, I would say at least 70% of the code ran in the application domain, okay? So you could see that even though they restructured it all into domains, whatever they couldn't figure out how to separate out, they stuck into this AP domain. Now, what they did was they functionally isolated the areas, right? So effectively, the domains, as we're going to see, no longer touch each other's storage or modify each other's control blocks. They quite literally have to communicate with one another to get them to do functions. And you could see these were the main domains that were created. Now, as IBM kept upgrading the product, we went through various different releases. You could see they continued to separate out function into domains. So Transaction Manager in the version 3.10 was within the AP domain, and notice they made it a separate domain in version 4.10. So they started by separating out more and more function. But over time, you know what happens. It's not separating out older function that you continue to do, but you add new functions. So just to jump here to release 5.3.0, you can see that all this stuff here on this line, this orange, was new functionality they added at version 5.3.0 internally, which was 1.3. And you could see if you separated it out, you could see things like document domain, web domain, socket domain. So these three domains were added for web support. You can see the resource recovery, which was added during that release as well, allowed you to do two-phase commit protocol with a CICS region and a batch job. And then over here on the left-hand side, you can remember IBM created BTS and added, 60 new API commands to CICS. And so they added the business application manager, event manager, and scheduler to support that functionality. And then over time, you could see we added Java, right? And toward the bottom, we added pipelines. So we could see a pipeline manager, right? Inter-system communication for your IPIC connections today. And then the last new domain that I've seen, and again, I don't know if we added one in 5.6. I don't believe we did, but I was looking back at version 5.4, we added the asynchronous services domain to support asynchronous services. So it gives you an idea of how many different domains there are, well over 50 of these things. And you may or may not be using every one of these. Let me go back for 1 second. If you have a system that's not using any BTS, then these three domains won't come into play during your normal application day. So anyway, CICS is organized into domains. Each domain is a single major component of CICS. And then the exception, of course, we're going to see is the application domain. So think of the application domain as old CICS, little mini old CICS running in new CICS, yeah? So what goes on in the application domain under the covers is pretty similar to the way CICS ran from the very early days in the 60s and 70s and 80s, right? So that domain internally is not restructured, but again, as we separate out functionality from the AP domain, we make that into separate function. So another example would be, let's say, temp storage, right? A very AP-oriented type function was separated into its own domain. But then you take a look at things like transient data, and transient data still lives within the AP domain. So anyway, domains never communicate directly with each other. If a domain needs data from one, it's going to issue this thing called the domain gate call. Think of it as a link with a COM area. Pass some data to a domain, get a result back. Calls between the domains are always routed through the kernel linkage routines, which is important because that means that trace data or dump data will kind of always show us where an application has been, right? Trace is really a history of where application has been if you have a copy of trace. But if you take a look at a physical dump in IPCS, you could look at things like the kernel stack storage, and it will show you the modules and what they called from there. So again, this is a better list of the domains with a little bit of documentation, which we left in here so that you can read at any time you want to. And I've already gone through much of these domains. I just take a look to see if there's anything else I wanted to point out here. Here's a good one for you, right? Directory Manager. So Directory Manager provides lookup services for resource definitions, right? But not all resource definitions have been moved to the new domain architecture. So the old table manager is alive and well, living in the AP domain. So depending on the resource type, we either use directory manager to look it up, or we use table manager. So a couple of things to point out also about domains. As you can see, they don't just get added, sometimes they get taken away. So IIOP is in a funny color there because Internet Inter-Org Protocol, the domain itself, has been removed, right? So at version 5, this domain went away because it's no longer a function supported by CICS, right? And again, you could look over time when some of these domains were added to the system. You can see there's one today for event processing, of course, right? What else is interesting here? Let's take a look. Yeah, well, manage platforms to manage applications, platforms, and policies. If you're using CICS in the cloud, right? It would go through the managed platform domain. Let's see what else is in here. Program manager is interesting, but we'll see a little bit about him later. And yeah, that's pretty much it. Again, you could read through some of this on your own a little later on. And yeah, that's what I wanted to talk about in terms of domains. So the next question becomes is how is a domain structured, right? So if you took a look at old CICS, right, the original version of CICS, right, it had a main control block, right? And if we could talk to one another when we were all in a room, I'd ask for the name, and somebody would certainly say the common system area or the CSA, right? You need to anchor all of the control blocks off of some central location, namely a anchor sort of block, right? And in the old system, it was the CSA. Well, in our new system, each domain must have its own anchor block, which is MVS getMade. Why does it have to have its own anchor block? Because we're going to see the concept of encapsulation. The idea is that since a domain knows where everything in its domain lives, but domains don't really look at each other's stuff directly, we need to have an anchor for each domain to find find its own control block. So every domain has an anchor block. And again, it'll have some state information, addresses of other control blocks, and it'll be a pointer through everything you want to see within that domain. Now, interestingly enough, the CSA, the original, is alive and well. Well, if you remember, I told you the AP domain is little mini old CICS running in new CICS, then where do you think it lives, right? The CSA is the anchor block for the AP domain. So let's talk a little bit about domain gate calls in this concept again of encapsulation, right? So each domain manages its own data and can't directly access another domain's data directly, right? So if you go back to the really old days, we ran into situations where when one management module would modify another management module's storage directly, right? So program manager, the program manager, well, I'll tell that story in just a minute, but each domain manages its own data, and therefore one domain can't directly modify it, right? So in the old days, it was like short on storage would require that two management modules would update each other's control blocks, right? Program manager and storage manager, right? But today, everything has to be done through a domain gate call, right? So what are domain gate calls and what do they look like? So if you take a look, the easiest way to see these things is through trace, believe it or not, right? Because whenever you look at a particular trace entry, you'll notice that at some point in time or another, it usually has some sort of 4-character identifier. You'll see things like SMGF, right? And what these are, they're actually management modules that provide function. So if you stick a DFH on the front of any of these things, right? That would be the name of the program that supports this particular function. So every domain has many of these, and not every domain has that many. You'll take a look at some domains if you actually take a look at something called the domain gate table, which will show you all the programs or domain gates that are available in a domain. You'll see some of them have as few as 2, and some of them are too big to fit in one row of the table, right? And AP being the biggest example of that. So anyway, Several gates, we can see the names. The two characters that start the domain gate call kind of identify who it belongs to. So if you could imagine, SM is storage manager. Now, if you go back to that first page I showed you with all the circles, you'll notice there was always a 2-character component code that identified the domain. SM was storage manager. If you ever need to look, just go back to that page and you'll see the 2 characters. Storage manager is a little strange because today we support 64-bit storage, right? So IBM created a set of programs that look just like the original ones they've had for a while, and they stuck in a 2 as the second character to identify it is the same module, but it does the work above the bar. So you could see SMGF, which we're going to see is for storage manager get main free main, as 2GF would be for storage manager get main free main above the bar. Now, you can also see SMAR for storage manager acquire and release storage, right? Every task that starts up goes through SMAR. So again, the first 2 characters generally identify the domain. And so you could see SM, and again, S2 being a special case of storage manager. And then there you can see the GF and the AR, get main, free main, allocate and release storage. Now, you can see there's some gates at the bottom here that don't actually start with SM, and we're going to describe those when we talk about generic gates, right? So standard domain gate call, what would it be? Well, I don't know. Let's see. I'm the loader and I want to load a program. Well, in order to load a program, I have to put it somewhere. Where am I going to put it? Well, I have to get some storage to put it in that storage, don't I? So I'm going to have to call the storage manager, right? And so again, that would be an example of loader calling storage manager with a get main free main request. So anyway, an individual gate can provide many functions. SMGF, as we point out here, can do both get main and free main functionality, right? So just because it's a simple gate call doesn't mean it can't do multiple functions. In fact, you might look, if you take a look at the domain gate table, which basically lists every row belongs to a different domain. It's a table, and every column is a different gate call, right? Basically the address of a program, such as SMGF. You'll find that some of the calls, the program calls, refer to the same program out of different gates, out of different columns. Why? Because they support multiple functions. Now, again, generic gates like DMDM are supported by many domains. We're going to talk about generic gates in a second. And you could look up whatever is available still in diagnosis reference in terms of domain gates and their function calls, although I believe that the Hello? Sorry, I got a warning.
Yeah, we just lost you for a second, Ezra.
Okay, yeah. I love technology, don't you guys? So anyway, this is, again, a little bit more of that documentation. So you could see gates and modules and macros here, right? So what we're talking about on this page is the fact that if you take a look at particular domain gate, like storage manager, get main, free main, SMGF, right? If you stick a DFH on the front of it, the DFH would imply that that's the program name, DFH SMGF. If you go look for the module, that's the name. There's also these macro calls, right? There's a DFH SMGFN. So a domain developer that wants to actually do a get main and get storage, like the loader wants to communicate with storage manager, he issues a macro call, right? So it's the same as the program name with an M at the end of it. Right? Makes it easy to remember it. And so if you do a DFH SMGFM and you specify the correct function, like I want to get main, this is how much I want. You also have to say where you want the storage from. And there's a couple of other parameters than I've identified here. The response would be an address of a storage area that you asked for, right? And there's an example of doing the same thing in 64-bit storage. So if you're interested in seeing what a 64-bit storage address looks like, there it is. It's address underscore address, right? So the macro call M is not for use by us, but it's obviously for use by domain developers when they're communicating with different domains through gate calls. We do actually have a form that we can use. There's a DFH, for example, SMGFX, right? If we were writing an exit within CICS and we didn't have access to the exec API, we could issue an exit call, exit macro. Well, I should say it's a domain gate call within an exit, and we would use the X as the macro call that we could use. And if you take a look, you can also see that DFH SMGF Y is the copybook that belongs to it. So we do have access to some of the functionality, but for exit use only, really. So again, this is an example that I've been describing all along, and this is just an example during XMAT, right, which is the transaction manager attach. At some point during attach processing, he needs a bit of storage, and because he needs a bit of storage, you can see that, you can see that he does a call over to SMGF, right, to do the call. And that just means he codes the macro in line. And if you take a look at the macro, whatever it might be, you'll see it puts the parameter list into register 1 and it branches into the kernel. So all of these macros, if you take a look at them, they're basically building parameters, and then they're doing a branch and link into the kernel, right? And somehow we get from the kernel to the storage manager, as we're going to see in a minute, right? Okay. So I've been talking mostly about specific gates, right? A specific gate provides access to a unique function, and it's easy to understand get main free main. Here's another example for you: dispatcher suspend resume, right? So when application gets suspended at a particular point in time, or suspends itself because it's waiting for a result from something. So a good example is dispatcher suspend resume. We've also seen storage manager get main free main, right? And this is called a specific gate simply because we ask for specific function, right? And it's one caller, one person gets control, and the response comes back to us. There is something called the generic gate, right? And for those that might know a little bit more about the domain gate table, it's in the early columns of the domain gate table. It's basically columns 1 through 9 that have the generic gates. And a generic gate is something that provides function to several domains pretty much at the same time, right? So a good example of this is statistics, right? Depending on your statistics interval, right? So let's say yours is every 15 minutes. You ask for statistics to be collected. The question is how many domains would care about providing statistics? Well, it's easy. If a domain cares about providing statistics, it provides a program that we can call during the statistics collection through the STST gate, right? So think of it as a broadcast message, right? You're actually calling multiple domains at the same time. Another example might be even a better example called the domain manager, right? The domain manager is responsible for startup and shutdown within CICS, right? So when CICS starts up, right, DFH SIP, eventually control is actually given to the kernel, right? And the kernel bootstraps the domain manager. And the first thing the domain manager does is it runs this DMDM gate, or initialization gate, and it asks all the domains to start up at the same time. It's called the horse race startup. And if you ever take a look at your JES messages when your CICS system is coming up, you'll notice that all of these domains are trying to start, initialization started, and then complete. And you'll see all these domains are trying to come up at the same time. The domain manager will actually track which ones come up, which ones don't, if they don't, and the time they start and the time they ended. The point is that when the kernel bootstraps the domain manager, the first thing he does is issue this generic gate call. Okay, everybody start up, right? And then he tracks the results all the way back. So that would be a generic message or a generic gate call that can be used. So it's pretty much a gate that is supported by multiple domains for some common function like statistics or startup. Then there's a reciprocal gate, or also known as a callback gate. I kind of like to call it the transfer of control, right? If you look at a domain gate call on average, everything you can think about, you always want control back to the next sequential instruction, right? So when we did that XM attach a few pages ago, and we said he calls the storage manager, what do you think happens? You call the storage manager, he gets the storage, and he gives you control at the next sequential instruction so you can continue processing, right? You know, so that is more or less, you always expect a call, a response back. A callback gate's a little bit different. I've only seen a couple of these, right? There's an example at the bottom of the page where Recovery Manager calls only the domains that have registered an interest in sync point processing for a task using the RMRO gate to commit or back out. Another example is between the dispatcher and the kernel. Because the kernel has to make sure you have storage and the right control blocks to run, he has to be called to make sure that your storage is all allocated. Let's keep it simple here, right? But the problem is who decides when you run? It's actually the dispatcher, right? Because some task gets attached and the dispatcher comes along and he says, oh, okay, now it's your time to run. Let me give you a chance to run in this system. So you don't have any storage. You've never run before, right? So the dispatcher has to actually transfer control to the kernel, because if you don't have any storage, you have no stack storage. I can't do a domain gate call where I can do the equivalent of link with a COM area because I got to stack the current program. So effectively what it does is it transfers control to the kernel through this callback gate, and then the kernel actually does a call back to the dispatcher and gets you running again. So it's kind of like a transfer of control. The easiest way to see this is take a look at trace. If you take a look at a task starting up, I personally believe the very start of any transaction, if you turn on all the elements of trace and you trace a bunch of transactions, you'll always see these DSKE task replies, right? And that's because there was a KEDS create task to the kernel, and then this DSKE task reply, right? So the KEDS is actually the reciprocal gate, and the DSKE is a normal specific gate call, and the task starts up. So the kernel is actually the oldest module on the stack in all cases. So that's just a little bit about a callback gate. The easiest way for me to think about it is quite simply as a transfer of control. Now, when one of these domain gates is used, it passes a COM area or storage or a parameter list, whatever you want to call it, in register 1. And the parameter list has a very specific format, as you can see on this page here, right? It has a 16-byte header, right? So we're looking at the 16-byte header. It has 8 bytes of existence bits. And then the first 4 parameters are always the same, yeah? Then the rest is pretty much variable depending on what that particular domain gate call does. So let's talk about this for a minute. The first 4 bytes of this domain gate call format parameter list, whatever you want to call it, is an LLBB. If you remember the old days of LLBB, it's 2-byte binary length followed by 2 bytes reserved. And then there's a format number, an version number, and 4 bytes of reserve. So that's pretty much what you would expect to see in a header, and overall length, then format, version number, and then reserved. Then you get these 8 bytes of existence bits. Since there's 8 bits in a byte, we know there could be up to 64 possible parameters. The bits here are just to indicate whether the parameter is passed. So this is a variable length control structure, right? Effectively, you have to determine which bits are turned on to figure out what fields come next, right? Now, in terms of these 8 bytes of existence bits, the first 4 are always set the same, right? Because the function is always there. So that's a 1 bit turned on. Then you get 1 bit that's always reserved, and then a 1 bit response and a reason code, right? So we have a response and reason code that always comes back. So this is 1, 0, 1, 1. So every existence bit will start with a B if you take a look at it. And I'm going to show you where these things come out anyway. And then all the rest of the parameters are optional. It depends what that domain needs to process the request that you've asked for. So any module calling a domain must use the correct format for the call. And again, the format represents the parameter list structure, and it describes the parameters and whether or not they exist. Now, in terms of the formats themselves, if we're talking about a specific gate, the format is owned by the guy you're calling, right? Because if you're calling me and I'm writing the program for you, I know what parameters you need to pass me so that I could do my job for you. And then I know what I need to pass you back because I kind of have an idea of what you were looking for, like storage. So every format is owned by the domain that you're calling. Now, it's a little bit different for generic gates, right? Because generic gates or the callback gate, the design is by the actual person that issues the call. He says, hey, you want to support statistics? No problem. I'm going to call you and pass you this data. You need to pass me back this data, and life is good, right? So there's a slight difference there. But anyway, the format, again, is owned by either the called gate or the calling gate. So we give you an example there. The formats for generic. Okay, let's go. Cool. So now let's talk about kernel linkage. So I mentioned this a little earlier, but I didn't highlight it as much as I probably could have. When one domain calls another, they don't call each other directly. So you see all these domain gate calls, and it gives you the implication that, oh, okay, I'm going to make a call, and the transaction manager is calling the storage manager directly. And the answer is that's not entirely true. When domain A calls domain B, what they actually do is call kernel linkage routines. So if you remember, I told you the expansion of the macros that generate the calls, right, will end up calling the kernel linkage routine, KEDCL. So it's DFH KEDCL if you want to know the program itself. Anyway, why is it calling kernel linkage? Because the working storage for the existing program that you're running, as well as the program that you're calling, lives on the kernel stack, right? And so that's why every domain gate call goes through the kernel, so that he can provide the storage through his stack for these calls. And interestingly enough, if you take a look at this picture, one thing that's different here than a standard stack that you might be used to is the fact that the originating module already lives on the stack. And what I mean by that is if CICS gives control to a program because you have tran A and it runs program A, right? Internally, CICS doesn't have a stack, right? Because, well, in the kernel it does, but within your application, there's no application stack when you're running your main program. But if program A were to link to B, CICS would be forced to put A on a stack and start running B, so that when you do a return from B, he can reload A and start running him again. So the only time we use a stack in the application world is when we actually do a link from one program to the other. In the system world, the stack exists from the beginning of time, and the very first module on the stack, right, starts the process, and it's always going to be a kernel module anyway. But as you can see through this picture, right, domain A calls B, right, B calls C, C calls, well, I guess we get to C and then we stopped over here. All of these go through the kernel linkage routines. His job is to carve out a new piece of stack storage. Stacks and CICS are made up of a fixed piece plus a variable piece. So stacks are variable in length. And then you'll notice that when we leave a particular domain, what it does is a BR14 branch on register 14, which would take us back to the caller. And in this case, the caller will be the kernel linkage routine. So that's pretty good. And then what he will do is unstack the last entry. It's a push down stack, reload the registers, branch to register 14. And the next thing you know, you're back in the program that called you. So it works very efficiently. It's very fast and very efficient. Nonetheless, that means the kernel is aware of every module on the stack or every system request that you might have made. And keep in mind, just for knowledge, the stack size is 28K on average, and that means that CICS will give you 28K in a fixed piece. And so this is a fixed piece of storage. There's 2-pointer moves to stack and unstack entries, which makes this very fast and efficient. However, every time in your application you do a program A link to B, you will invoke a system module within Program Manager to actually make the whole process work. And therefore the stack grows and shrinks based on what the application is doing under the covers. So again, because we use the kernel in this manner, he provides a consistent linkage and recovery environment for CICS. Application programs have no external interface to this linkage. However, you can actually see it within a system dump, right? So if you get a system dump and you take a look at the kernel, you can see whatever's on a particular stack. Now, the better way to do it is trace, right? Because the associated trace entries, if you have it, will show you where you've gone through time. The stack itself only shows you a snapshot in time at the time of the failure, right? So I've looked at kernel stacks for problem determination, and I've found that I've missed things, because if you look at trace, you'll see that the stack can grow, the stack can shrink dynamically, and when you take a picture of the stack in time, there is no history there. You don't know where you've been over time. So again, a call is made through the kernel linkage routines using general purpose registers at the time of the call. Parameters are stored in the kernel entries, and return is just a BR14. So here's an example. Figured I might as well show you one of these. This is a dispatcher suspend resume gate call, right? And this is used to suspend and resume tasks, right? In fact, if you take a look, there can only be one task running on the QR TCB at any particular period in time. You might have some L8 TCBs, but in an average CICS region, you'll see there's always some transactions suspended, right? Which will end in something called a DSSR pop task, which means the guy is suspended. What I'm showing you here is effectively the parameter list. So you could see the parameter list with a 2-byte length, 2-byte reserved, format and version number, right? And then you'd see the existence bits, right? So there's DSSR existence, and you could see there's the 80-bit. Notice the 40-bit is missing. Remember, I told you that was a reserved area. So the 80, 20, and 10 for function, response, and reason code. And then you could see some fields in here, a DSSR suspend token, an MQ wait type, a resource name, right? And then you could take a look at the different functions that are available. So you could see DSSR add, suspend, delete, suspend, resume, and some of the old wait types. And then there's response and reason codes, which we'll talk about in a minute. In fact, we'll talk about it right now. So the first thing to note, that when you get response from the kernel, you'd see that we don't use the value of 0, 0. Yeah. A normal response to an application request is a 0, 0, right? But we use 0, 1 as saying that the function completed successfully, response is okay. The reason IBM uses 0, 1 is to know that they actually issued the function or not. Because if a failure occurs, we can't tell whether or not a response was received. So the field's initialized to 0, 0, but the response is 0, 1. Then you get the standard types of errors: exception, disaster, an invalid parameter list. It's kind of hard to get one since you're using domain gate calls. They should never be invalid. Then comes the interesting ones. A hex 05 is a kernel error. Notice there is no reason code set. Well, if you remember, I mentioned this domain gate table, which has the addresses of the modules for each of the domains gate calls that we're going to issue. So as part of that macro definition, for example, DFH SMGFM, when the macro expands, it puts in what we call row 2, column 10, because that's where the address of SMGF lives, right? When we get to row 2, column 10, we branch to the address in SMGF, and that's how we load the module, right? Well, the way CICS supports functions that are not available is through this kernel error. So, you know, you don't have to have every function running in CICS. You could bring up CICS with TCP/IP equal no, right? And then you wouldn't have any TCP/IP services within a CICS region. So when we take a branch into the address of where a module is supposed to live, we could either see the module itself, or we could see the kernel error routine, DFHKE-RKE. If we hit the kernel error routine, we will get back what we call a kernel error. Now, is that a significant error or not? Well, if I was looking for a function that was optional, I wouldn't consider that a significant error. But if you're looking for a function that should be there, like storage manager get main free main, the CICS region would come down so fast it would make your head spin. So again, kernel error, we don't need to set a reason code because we know what it means. The module you're looking for isn't there. Now, if it was supposed to be there, that's a catastrophic failure. And then my favorite in Hexo 6, purged, right? Over the years, we've always been figuring out how to purge things faster and faster, right? If you're a sysprog, that's the first thing you love to do is kill things, purge, kill, right? In fact, IBM invented kill, didn't they, recently? So do you ever think about what happens to the stack when you kill a transaction that's running? There could be 15, 20, 30 elements on the stack, and you're way down deep in the muck and mire. Next thing you know, some sysprog comes along and kills your task, right? Well, we have to do back out gracefully, otherwise the whole CICS system comes down, and I don't think we'd want that. So what it does is it allows us to return a purged, which every domain gate call, I guess, must understand, to gracefully get out of something that you're knee deep in, right? So that we can purge a task. That's the type of reason code you get back, okay? And again, this is just showing you the parameters and the gate call itself and some of the optional parameters. And we're going to see an example in storage in just a second, right? And now this is just an extract again. Remember, we showed you the existence bits. Now we're showing you the size of the fields that hold the parameters themselves. So a function is still only 1 byte. Response and reason codes are 1 byte. But notice the DSSR suspend token is an address length of 4. The MQ wait name is a length of 8. The resource name and type are 8 bytes in length. So even though you have a 1 byte indicator whether the field is there, a 1-bit indicator whether the field is there, you still have indicators with bytes to hold the values themselves. Now, where can you see this stuff? In trace, right? In fact, if you ever look at a full trace, the first thing you'll see is the data area, the very first data area that you get back in full trace is the parameter list. If you look at any domain gate call, right? So this is a DSSR. So if you're looking at this full trace entry, this is the trace point ID, DS0005. This is the module. Remember, just stick a DFH on the front. That's the module you have. Now, this is an exit, right? You could have trace entries on entry and trace entries on exit. This is a exit to a wait old W, which is an old wait type. People like terminal control use it, and you could see the response is okay. Now, if you ask for full trace, the element that you get first with the 1-, and you know in trace you can get a 1- and a 2- and a 3-, depending on the number of areas that are returned in trace, you can see a bunch of data. But the first one will always be the parameter list. Now, remember the length, LLBB, so there you have it. The length of this is certainly hex 70, no question about it, right? Now, again, the length includes the length of the LLBB itself, and this asterisk should be on the right. So this is not in our area. I got to fix that, sorry. So then you get the format and version number, and then you get existence bits, and this is where it gets interesting. B, I told you it would start with a B, 1011. Function, response, and reason code. And then you could see how many parameters were physically passed. There's a 1 and a 1, which is 2 bits, a Charlie, a C is 2 bits, a number 2, which is 1 bit, and then a 4, which is 1 bit. So if you look at this, there were 6 parameters passed. And then comes the rest of the parameter list. Now, again, you'd need the copybook, DFH, DSSRY, to figure out what the different parameters are, but we've given you an idea of what you have here, right? And so you could see the parameters that are passed back. And this, of course, is terminal control, waking up from his long sleep. Yeah. Now, do you have to do this type of analysis every time? Oh, heck no, I'd blow my brains out before I do that. If you have to do this on every trace entry, you certainly wouldn't enjoy life. So you only have to do this on rare occasions if you really even want to. So let's talk about core domain control blocks. Well, to start out, let me point out that, again, you have to know the difference between a transaction and a task, and hopefully you do if you're sitting through internals right now, right? But each task is what we're really interested in the world of CICS, right? So when we're tracking it under the covers, we're tracking the tasks, not the overall transactions, right? Now, in order for a task to exist in our system, it needs a certain amount of control blocks. You'll see that there's a kernel task control block, right? KE task. There's a dispatcher main control block called the DTA, or a dispatcher underscore task. There is an XMTXN control block, which is short for transaction manager transaction control block. And there's usually an AP domain control block, which we'll see in just a moment, right? And in order for you as an application to run in the system, you will have to have at least these 3 or 4 control blocks. The AP domain control block is actually just the TCA. So anyway, the first thing to point out is when you're looking at tasks themselves, they fall into various categories. There's a system task and a user task, or which we call a user transaction, right? The system tasks themselves, you might find they only have a kernel and a dispatcher control block, a kernel task and a dispatcher task control block. Unless it exploits the exec API, it won't have the transaction manager control block or the AP domain control block, which is the TCA, right? And so when you're actually looking under the covers, not every task will have a XM control block or a TCA. Now, why is that important? Well, because you look at tasks, and if you look at IPCS formats of dumps, you'll see it says system and non-system task. So a system task generally does not have transaction manager, which means if you go look at the transaction manager output in IPCS, generally you won't see those system tasks. But there are some system tasks that need to do the exec API, and those will have TCAs and XMTXNs. So kernel task, what is it and what do we care? Well, the kernel task, or TAS entry as its nickname is one of the most important control blocks. It represents work through the kernel. Every task in the system must have one of these. From the kernel task, you can get to the stack entries. You can get PSW and register information. You can get ABEND information, and it's used quite heavily up front in first failure data capture. Okay, so the kernel is pretty important. When I have a system dump, the first thing I do is I go to the kernel. If I have a program check, ABEND, or loop, that's the best place to start because I get an idea of what was running in my system at the time of a failure. Dispatcher task, everybody needs one of these too because he's the guy that makes sure that you get dispatched on a TCB. If you never get dispatched, you're never going to run in the system, so you're going to need one of these. Now, the official name is DS_task, but we call it a DTA, or dispatcher task area control block, and it represents the workload in the dispatcher. Now, a lot of people have asked in the past, why don't they just share a control structure, right? Why don't the kernel and the dispatcher use the same control block, right? And just stick all the information in one place. Well, if you remember, encapsulation of the domains does not allow that. So if a domain needs to track a transaction through its life, it's going to have a control block that manages that, like a DTA for the dispatcher, a kernel task for the kernel. Now, not every domain manages tasks. Sometimes they manage different things, like storage manager manages storage. Yes, it does also manage tasks, but it manages storage as well. And so therefore, it might need additional control blocks to manage those storage areas. So again, dispatcher task, it keeps things like priority if you're running a priority-oriented system, state information. It's a good place to start if you have waits and hangs in your system, or you're not getting the response time you expect. There's a troubleshooting manual. I updated it, the link for 5.5, which describes the various different wait types for transactions, which is interesting. Now, transaction manager, again, not everybody has one of these. So this is the first separation point, right? You won't have one of these if you're not a transaction and not doing any AP type work. So again, what is the XMTXN for? It contains things like transaction priority, it has the transaction number, and effectively the transaction manager can be used to hold up tasks if you're in a max task situation. And he's also used for tran class limits. So he provides with tran class support. So he'll hold up tasks that want to enter a tran class that is full, right? And he'll let them go again when they're ready. Now, he also maps a whole slew of other control blocks, right? So from the transaction manager, you can get to things in the AP domain and the program manager and the recovery manager. Storage manager transaction. Everybody needs one of these too, because everybody gets storage out of 6 subpools today, right? Depending on your release of CICS, it's really hard. You got to look at the individual release, but at 5.5, there's storage you get from 2 areas below the line, 2 areas above the line, and 2 areas above the bar. And so this SMX control block is the anchor for all the storage associated with an individual task. So we'll have things like the transaction number, the subpool information, and the key of your different storage areas. And again, it's useful if you're looking for things like storage violations or short on storage conditions, i.e. looping tasks that exhaust the variable storage. Now, this is just to point out that obviously this release, CICS 5.4, and as we move up, more and more things are going above the bar. Right now, we don't use too much storage above the bar unless you're in the world of Java, right? But over time, I expect to see more and more things go above the bar, and therefore, obviously, we're going to see more stuff there. So a little bit of a note as to how much storage you have. Remember, we had 16 megabytes below the line. Then we had up to 2 gigabytes above the line. And if you go into the 64-bit range, we have 16 exabytes of storage, roughly 8 billion as much storage as we had before. So I hope we're not going to run out this time, but who knows? You know, bad coding design, you never know. I'm just kidding, right? Okay, so anyway, at CICS TS42, that's when we enable the 64-bit mode, and now you could find various things above the bar, like the trace table, temp storage, other things like that. So IBM started by moving the large storage requirements above the bar. So we finished this up a little bit with the AP domain. Remember, everything that isn't a domain yet still lives within the AP domain itself, and so for example, it supports all your exec CICS commands. And if you take a look at the AP domain, it controls 3 rows in the domain gate table. Now, I did mention that you have a row in the domain gate table, a separate row for each domain. But what I didn't mention was, oh, that's right, AP uses rows 16, 17, and 18, right? Because again, he has to have enough room to stick all these module addresses in, right? Now, again, exec CICS interface is just how you do exec CICS commands. But other things that still live within the AP domain are application services like BMS, if you're still doing that. EDF lives there. You have the command interpreter. And look, event capture is something new. Why is it in the AP domain? Well, what events do you really want to capture? Events that live in the AP domain. So unfortunately, they had to write it into the AP domain. Now, all the intercommunication facilities, with the exception of IPIC, live in the AP domain. So DTP, function shipping, transaction routing, would be nice if that was all rewritten for IPIC. We can get some thread-safe mirrors on MRO, but never mind that. In the meantime, the older functionality for intersystem communication lives in the AP domain. IPIC itself has a separate domain, the intersystem domain, to support the new function. Now, you could see things like dynamic allocation, CEMT, CETA, the sign-on and sign-off transaction all live within the AP domain, okay? So this is kind of a summary. The 2 ones that I find really interesting are, of course, file control, interval control. None of those have been made into separate domains yet, right? But, you know, watch this space. You just never know when they'll separate it out into its own domain. Terminal control, I doubt will ever be its own domain because nobody cares, right? But transient data, as I mentioned earlier, is still in the AP domain. And then some of the system reliability functions like dynamic backout and emergency restore and key pointing all our functions within the AP domain. So you could see that still there's quite a bit of functionality within the AP domain. Plenty of room for IBM to separate out into separate domains, should they choose to. So hopefully that gave you an idea of the structure of CICS, how domains work, a little bit about the domain gate calls. Keep in mind, you can look at some of them now in trace. If you collect a little bit of trace, it'll show you things like kernel linkage, and hopefully we gave you an idea of how some of the core domain control blocks are used and worked. So I will leave that open to discussion or any questions.
Don't really have any questions on the chat yet, Ezra, but just for me, IPIC, or IPIC as I often say, I don't know if that's a
you can call it
transatlantic thing. Are you a fan?
Wow, God, it's funny. No, I'm not a fan. Cool. I mean, I think it's a good start, but like everything else, I think that IBM comes out with stuff in CICS, yeah, and then over time it becomes really resilient. And I can give you at least, I don't know, 5 examples of stuff I would never use, like vSAM RLS when it came out, but today I would, right? And IPIC falls into that category. It's flaky. The connections come down too often. There are 2 controllers on each side to make sure the session is up, and still it doesn't manage to keep the session up all the time. I don't know why that is the case. And the only advantage of using IPIC is getting thread safe without TCP switches, right? You can get file control thread safe, right? And not local file control, right? But for that, I moved to RLS anyway. So the fastest thing is cross memory within an LPAR, right?
Yeah.
So, so what is IPIC buying you other than, like I said, headaches? And right now, that's what I'm seeing with IPIC. If it gets better, I'd be the first guy on board. You know me, right? So
I'm just seeing potentially being forced down even within a Sysplex, being forced down a HTTPS route by our standards and our security people, which I just see as another overhead. Not the end of the world.
But I never understand why
controllers does worry me. I didn't realize that was an issue. But certainly, obviously, if you're going to have ZOS Connect, IPIC connections kind of come with it. I know you can get a CICS Liberty version, but if you're going to exploit other subsystems, it's probably not a strategic route that most people are going to go down anyway. It's a very CICS-centric route.
Yes, it is. But so what? CICS is the master of the universe. So from CICS, you can go anywhere as far as I'm concerned. So I prefer that route. I mean, that's just me. But I agree with you. I would like to see IPIC get a little bit better, a little bit more stable. I have customers running, every 5 seconds to check the availability of a connection. It's crazy things that they're doing. And it's the world of TCP/IP. It's not a point-to-point connection, right? So it's the world we live in. So we're trying to take the great functionality we got from SNA and how we developed it over 40 years, and it worked perfectly. And now we're trying to take TCP/IP, because the world is using that, and stick it into something that worked better the other way around. I would love to see thread safe mirrors in MRO and ISC, but I think if IBM gave us the thread safe mirrors without TCP/IP connections, nobody would ever use the IPIC connections. So that's the truth. The only people using IPIC today or trying it are trying to get thread safe mirrors, right? That's it.
Yeah.
Because it's slower and it's flaky. As soon as it becomes less flaky, I'm not even worried about the slower. I just don't like the flaky.
Good answer. Thank you very much, Ezra. I can't see anything else in the chat. This is our last session, and Nick won't forgive me if I don't tell you that you had the record number, beating me by 2. I was thinking of stopping the count like Donald Trump, but unfortunately.
What was the record number?
46.
Excellent. Very nice.
Yeah. So I hope everyone's enjoyed the overview. You know, it is a complex subject, CICS internals, but I do think that you've framed it at a technical level, but also at a high level, so people can overview it. And I love the bit where you start to link what we've got in the domain names and the gates into the trace, because I think that sort of shows everything and where you can go and see things as they actually happen.
Absolutely.
So, it's a really good presentation, and thank you very much for your presentations. Thank you to Nick Garrett from IBM for supporting me, Steve Foley, Jenny He, Will Yates, and all the other presenters that we've had. I think it's been a really good session. We've reached more people. I'm desperate for feedback from everyone. So everybody on the call, if you can give feedback externally, GSE. I know we've got a few NatWest folks on the call. Any internal feedback you can give, and hopefully we can kind of make this a thing for next year. That would be my goal, along with any face-to-face things that might come along. I'm just checking the chat again because there's a few more comments. Lots of feedback, so really good. Thanks very much, everyone, and I hope you have a good run up to Christmas and all your systems stay up, and we'll speak soon. Cheers, everyone, and thanks again, Ezra.
Cheers. Anytime.